aren't those. Let's try this again. All right, practice exercise 34 in your practice exercise booklets. On this one here, no calculator needed. What you're going to do is round off each of the numbers you're given. You're given some crazy ugly decimals, which frankly in life a lot of times we deal with crazy ugly decimals. No, we don't. We round them off to whole numbers, and then we do math with nice, easy whole numbers. So for instance, if I gave you 7.814 times 3.17, well, I'm not going to use 7.814 class. I'm just going to round that to 8. And I'm going to round that to 3. What's 8 times 3? This answer is approximately 24. May not be exact, but it's pretty close. Make sense what we're doing? Okay. Just rounding off. Now, if you should work a problem, for instance, let's say this were let's leave it this way. Let's say we're a division problem. Well, what's 8 divided by 3? 2 2/3, right? But round that up as well and say, well, it's kind of 3. Instead of saying 2 2/3 or 2.6 repeating, round the answer if it doesn't come evenly to a whole number also. So round to whole numbers, then do the math. If the answer doesn't come out evenly, round it to. No calculators. Exercise 34, begin. Way to go, guys. Clean sweep. As long as one you got it right, because if we got all of them actually wrong and a girl still ends up winning, that's a bad look, so. Not sexist or anything. Is that done this. Go ahead and take a look at these together. Chris, you were first going across the top row. You rounded off the numbers, you multiplied, you got 78. For the next one, you rounded off the numbers, you multiplied, you got $7,200 or $7,200. For the next one, you had to round off all three numbers, then multiply them to get 22,920. Good. Next row going across. We rounded the numbers, we divided them, we got good. Initially 235.1, but yeah, 235. For the next one, you rounded, you divided, you got $400. For the next one, you rounded, you did a division, then a multiplication, and got 100. Bottom row going across. You rounded off the numbers, you multiplied, and got
140.
For the next one, you got
7.
And for the last one,
63.
boom, got them all. Unfortunately, I'm out of candy, but your neighbor's going to take care of you this weekend, so just go see him. I've already asked him to have some candy waiting for you, okay? So we work things out with your neighbor. I'm just kidding. I'll have candy for you. I'm just going to go get
for
some.
another mile.
All right. Now, anyone else get them all correct as well, just not as fast as Chris? Genesis, you did. Kendall, you did as well. Okay. How many maybe just missed one? All right. Questions on the exercise, because this is really how you're going to do math the rest of your life. You got a calculator on your phone, but let's be honest. Who wants to pull that out? You know, you just go like, yeah, eggs are $2.88. They're $3. You know, especially when you factor in tax and stuff, it's $3. Let's move on with life, you know, doing your math that way. All right, let me go and collect those from you. Take out your notebooks. And we are going to press forward in our study of geometry, continuing to look at this idea of parallels today. Continuing to look at the idea of parallels today. Theorem 24 in your notebooks. Theorem 24 in your notebooks. Theorem 24 says this: if three or more parallel lines cut off equal segments on one transversal, if three or more parallel lines cut off equal segments on one transversal, comma, then they will cut off equal segments on any other transversal. If three or more parallel lines cut off equal segments on one transversal, then they will cut off equal segments on any other transversal. If three or more parallel lines cut off equal segments on one transversal, then they will cut off equal segments on any other transversal. Once you have that down, turn to the proofs of theorems corollary section, new sheet of paper, at the top of the paper, Theorem 24. 3 plus parallels cut off equal segments. Just kind of abbreviate it that way. 3 or more parallels cutting off equal segments. Now, before you put anything else on the paper, here's the idea. If I have a whole lot of parallel lines, they don't necessarily have to cut off equal segments on a transversal, correct? We can clearly see we have a little segment, a medium segment, and a big segment. But if they're spaced out just right, like for instance, presumably the blue lines on your paper are spaced out just right, where if you were to draw a transversal, they'd cut off equal segments on that transversal. If that's true, they would cut off equal segments on any other transversal you decided to draw. You'd have equal segments, equal segments, equal segments. You get the idea, right? Not all equal to these segments, but the segments would be equal to each other for that transversal. Make sense? Again, it's more or less intuitive anyway. So if you would, maybe using the blue lines on your paper, go ahead and draw 3 transversals. And let's call them X, Y, and, or 3 parallels, excuse me. Go ahead and call them X, Y, and Z. I drew 4. I can't count.
I did too.
X, Y, Z. So we 3 parallels. Again, it works with more, by the way. It's just the proof's a little easier if you only have the 3. But you could, the way we do the proof, you could do this with as many parallels as you want. Go ahead and draw a transversal, call it T. And let's mark equal segments here. We'll call the points of intersection A, B, and C. Notice since these are points, these get capital letters. Lines labeled as such would get a single lowercase letter or capital letters for the endpoints. Let's draw another transversal. I'm going to draw at a very different angle. I'm going to call this one R. Now let's call these points of intersection M, N, P. We want to prove that if these segments are equal, then these segments would have to be equal to each other. Again, not to these two, but to these two. Am I missing something? Oh, all right. That's me not knowing my alphabet. All right, so here's what we're given. We're given X parallel to Y, parallel to Z. With transversals T and R. X parallel to Y, parallel to Z, with transversals T and R. We know that AB equals BC on T. So we're given equal segments on one transversal. We're going to prove that that's enough to get equal segments on another transversal. We want to prove then that MN equals NP on R. We want to prove that MN equals NP on R. Once you have that down, 2 columns, statements, reasons. And X parallel Y parallel to Z with transversals T and R. And we know that AB equals BC. Well, as I look at the proof, I'm trying to ultimately prove 2 line segments are equal to each other, correct? That's ultimately what this boils down to. If I get 2 lines equal, proof is done. How do we normally get lines equal?
Angles.
If I could get the 2 lines opposite equal angles in a triangle, correct? Is there any way to get these 2 things in the same triangle so they'd be opposite equal angles? No, but that's a thought, right? That would have worked. How about another way to get lines equal besides showing their opposite equal sides in a triangle? Ethan? We've been doing this for months now. Come on now. CPCTE after we get some triangles congruent. Only problem is MN and NP, they're not in triangles, right? They're in these funny looking, they're not even in parallel, there's 4-sided figures here, right? They're not in triangles, yeah? We could make a triangle? Just one triangle?
We can make 3 triangles.
We can make 3 triangles? That's a lot of triangles. What triangle were you thinking?
Draw a line.
From where to where?
Let's call it point D. Put it to the right of R.
D over here somewhere.
A little bit up. And then just cross through.
D goes right here, and we do what with it?
Just cross it diagonally down the...
Like that.
Yeah. Up a little more to where it cuts off between R and M as well.
Between R and M, up here?
Yeah.
Well, if we're gonna make a triangle, and we wanted to use CPCTE, wouldn't we want MN to be a side of the triangle?
You just start at M and then just then go.
So start at M and just draw a random line
No, draw, yeah.
like that. And now I've got a little triangle here, and then I have a triangle, but now NP isn't a side of a triangle. We're really close to the idea here. How about we do this? Let's go and draw two lines. One from M and one from N, but let's not draw them just randomly. Through a point, one and only one straight line may be drawn parallel to a given line. Let's draw our line so it's parallel to T in each case. Let's call this J, and let's call this K. And let's go ahead and say, let's draw, so you were close there, Chris. Let's draw MJ parallel to T and NK parallel to T. Because through a point, only one line may be drawn parallel to a given line. Through a point, only one line may be drawn parallel to a given line. So we draw a little parallel here and a little parallel here. Now thoughts on this for a minute. I just drew two lines, both parallel to the same line.
They're equal.
Ooh,
But they're parallel to each
they're
other.
parallel to each other. That probably is going to come in handy later. I don't know for sure, but MJ will have to be parallel then to NK because I just said it.
Because lines parallel.
Lines parallel to the same line or parallel to each other. Lines parallel to same line are parallel. Kind of like lines perpendicular to the same line or parallel. But here lines parallel to the same line or parallel. All right. Something else that I think is interesting here is when I drew these parallels, notice I have parallel lines. A, B, and MJ are parallel, aren't they? And they're included between parallel lines. What do we know about parallel lines included between parallel lines? They're equal. So therefore, A, B, and MJ must be equal. For that matter,
BC must be equal to NK.
BC and NK must be equal because they're parallel lines included between other parallel lines. So BC must equal NK because parallel lines included between parallel lines are equal. Wait a second though. Look at the given and look at number 4. Thoughts?
Oh, substitution.
Yeah, what could we state by substitution here, Ethan?
MJ equals NK.
MJ must equal NK because these quantities are these quantities are equal to equal quantities. Quantities equal to the same quantity are equal to each other, or in a word, substitution. So then, why did we draw these lines again, Audrey? It was Ethan's idea. To get a couple triangles that we could get congruent. Hey, we got a couple sides equal here. Right? So what else do we have to do to get them
Don't we only
congruent?
have one side equal?
I've got this side equal to this side.
Oh, sorry.
That's all I've got. I got a side in one equal to a side in the other. So that means I need to either get some more sides or some more
There's an angle.
angles. And I've got parallel lines. Generally, if I've got parallel lines, there's an easy way to get,
Opposite interior angle.
well, in general,
Oh.
equal angles. That's the Klein response to parallels, right? So I've got a whole bunch of angles here. Let me call this angle 1, 2, 3, 4, 5, 8. This point right here is a real problem for you. Hey, and right up here, Audrey, we got you at the top. All right. Oh, and Jamie's right here. I don't think anybody else is there. No, nobody else. Anyway, all right, so what angles could we get equal to each other? Chris?
3 and 8.
3 and 8. Why are 3 and 8 equal?
Because angles opposite equal sides are equal.
Ooh, that's not, we never proved that.
Angles opposite parallel.
Ooh. These angles are both above their respective parallels and both to the left of the transversal. They're in matching positions. They are corresponding angles. And if you have parallel lines, corresponding angles of parallel lines are equal.
We never proved that.
We never proved what?
What I said?
No, we proved that angles opposite equal sides in a triangle are equal. We never proved angles opposite equal sides are equal.
Can we prove that, or is that possible?
No, it wouldn't be provable. We'd have to have in a triangle. So angle 3 and angle 8 are equal to each other because corresponding angles
And parallel lines.
of parallel lines are equal. Corresponding angles aren't necessarily equal unless the lines are parallel. Hey, look at this. I've got sides equal. I've got angles equal. I got to get another pair of sides somewhere, right? Or another set of angles, right? I'm sorry?
MN and PN.
MN and PN, I would love to get them equal, Ethan.
Well, if we get them equal,
Then we'd be done with the proof anyway, right? So if there was another way besides congruent triangles, then forget the congruent triangles, right? Quentin, haven't heard from you yet.
MN and P be equal.
By the way, if they were equal, sides, angles, or side, angle, or worse yet, angle, side, nope, can't have that. So no, MN and PN wouldn't work to be equal. In fact, even these two sides, that'd be side, angle, or angle, side. So it can't be another pair of sides. It's gotta be another pair of angles, right? Because if I could get like 2 and 5 equal, side, angle, or 1 and 4 equal, side, angle. So it's either gotta be 1 and 4 or 2 and 5.
1 and 4.
Okay, I'm hearing a 1 and 4. Let's see if Quentin knows how we could get 1 and 4 equal.
I think 2 and 5 would work.
Well, somebody else said 1 and 4, so we're going to see about those first. Is there any way to get 1 and 4 equal?
Well, you drew a 1 to 1. Would it be corresponding?
Well, the problem is, right, if we've got this transversal here,
Oh, yeah.
they aren't formed by these parallel lines, are they? Right? They're formed by these two lines. Oh, wait. These two lines are parallel. So if I just kind of turn my head sideways, or you could turn your paper sideways, I do have parallel lines cut by a transversal. These are both above the respective lines and to the right. These are, in fact, yes,
Equal angles.
because they're corresponding angles. So for the same reason we got 3 and 8 equal, now we were looking at these parallels. Now we're looking at these parallels, but 1 and 4 are equal for the same reason. They are also corresponding angles of parallel lines. So they're equal, and guess what we got now, class? By, side angle. The sides aren't included between the angles, it's side, then 2 angles. So by side angle, yeah, those triangles are congruent. Audrey, how would I name my congruent triangles here? Triangle MJN is congruent to triangle NKP. All right, and why did we want these triangles congruent all along, Ethan?
So MN equals NP.
By,
CPCP.
there we go. So MN equals NP by CPCT. And there we go. And again, this is reproducible because if there were another parallel, you understand we would have drawn another little line parallel that would have been parallel to all the others. And we would have had corresponding angles all the way down. And with these parallels, corresponding angles all the way up. And of course, if these 3 sides are equal, and these are all equal to these, then they're equal to each other. So again, as many lines as you want to draw that are parallel, if they cut off equal segments on one transversal, they'll have to keep cutting off equal segments on any other transversal. Question?
Could you prove 2 and 5 to be right angles using right angle?
I have no clue if they're right angles or not. I don't think so. This doesn't look perpendicular, and if these are parallel, then these couldn't be perpendicular either.
Well, we don't trust the right, but like, could you use like angle like potentially?
Is there anything in the given to indicate we do have a perpendicular or a right angle anywhere? So if it's not in the proof that, even if it kind of looks like a right angle, if it doesn't say anything about a right angle, or even like, okay, if there were like a way to get these two angles equal, then by definition they'd have to be right angles. But there's not even any indicator of that, so no right angles. Really 2 and 5, they are equal by CPCT, but there's no way to get them equal before CPCT, kind of like the M and NP. Good question. Corollary 24-1, flip back to theorems corollaries section. Corollary 24-1. Corollary 24-1 says this: a line parallel to one side of a triangle, a line parallel to one side of a triangle, a line parallel to one side of a triangle that bisects a second side, a line parallel to one side of a triangle that bisects a second side also bisects the third side. A line parallel to one side of a triangle that bisects a second side also bisects the third side. A line parallel to one side of a triangle that bisects a second side also bisects the third side. Once you have that down, turn to the proofs section. Go right back to that paper you were just on, but on the back side of that proof. Corollary 24-1. So on the back of the theorem 24 proof, corollary 24-1, line parallel to one side of triangle and bisects second side, therefore bisects third side. Line parallel to one side of triangle and bisects second side, therefore bisects third side. Once you have that down, go and draw a triangle. Any old triangle, doesn't matter. You can even, you know what, we never do obtuse triangles. Let's do an obtuse triangle just to be really random here. I don't have that in my notes, but you know, hey, why not? Let's draw an obtuse triangle. They never get any love. They always feel left out and weird. Okay? And there's a reason for it, because they do kind of look weird, but you know, you don't want to leave them out. Just because you're weird doesn't mean you have to be left out, right, Ethan?
Yeah, I know.
You better say something.
And let's call our triangle ETJ, since it looks weird.
Alright.
Since jets look weird sometimes when you're lining them up. That wasn't a save at all, was it? All right, and we want to draw a line that runs parallel to one side. Now the easy way to draw this is to make it parallel to ET. Okay? Now there's an infinite number, don't draw this yet, of parallels you can draw to ET, correct? But we know this, that let's just say EJ only has one midpoint. One point that would divide it into two equal segments. And through that point, there is only one parallel that can be drawn. And I didn't draw it. But we don't trust our eyes, so I did draw it, okay? Just for the...
Okay.
There we go. All right. So this is going to be my line that's going to be the parallel. Let's go ahead and call it P. And what I want you to do is locate that midpoint, if you will, of EJ, that bisection point, and draw the parallel through it. Good news is you don't have to trust your eyes. So if it looks bad, it's not really bad. It's just that your eyes think it looks bad.
Oh, okay.
Yeah. It's like, I'm not ugly. Your eyes just think I look ugly. But don't trust your eyes. I am good looking. All right. And we'll call this point of intersection here M. And we'll call this point of intersection here X. Just be random. All right. So here's what we're given. We're given a triangle, ETJ, with P parallel to ET through M. We know that P at M. So we're given a line parallel to one side of a triangle, and it bisects a second side. So it's parallel to ET, but it bisects EJ. We want to prove that P bisects the third side, TJ, at X. We're going to prove that P bisects TJ at X. Once you get that down, 2 columns, statements, reasons. And we've got triangle ETJ with P parallel to ET through M, and P bisects EJ at M. Clang, one of our oldest clangs. Audrey? Well, that is a clang, but it's not one of our old clangs, and we're actually not going to use that clang the way we normally would, right? Normally, parallel lines, equal angles. We're actually going to do the whole proof without any equal angles. So how about the other clang that you see? Well, I didn't say midpoint anywhere in here. Bisects, right? But it means kind of the same thing, right? What must be true if P bisects EJ at M? Audrey? JM and EM are equal. Reason? Right, you knew when you saw bisector, that meant divided into 2 equal parts, so definition of a bisector. So EM and JM are equal. Now here's the thing. This is a corollary. Genesis, the fact that it's a corollary means I should probably prove it how? Previous theorem. And what was the previous theorem we just proved? Three or more parallel lines cutting off equal segments, right? Well, Genesis, I ain't got 3 or more parallel lines. I only got 2 parallel lines, right? So what do you think we ought to do, Genesis? Let's draw another parallel. Now, where should we draw the parallel so that our 3 parallels could cut off equal segments? In between P and E. So right through here? Maybe, but I've already got 2 segments that are equal. If only there were a parallel that went through J. Does that make sense? If I were to run a parallel through J, I would have 3 parallel lines cutting off equal segments on one transversal. Let's do that. Let's name this one G. And number 3, let's go ahead and draw G parallel to P through J. Draw G parallel to P through J. And we know that only one line may be drawn parallel to a given line through a point. So through J, there's only one parallel you can draw. I'm telling you that G is that one and only parallel to P. But if G is parallel to P and P is parallel to ET, what else must be true? Quentin? G is parallel to P, just prove it that way, given P and ET are parallel. G has to be parallel to ET. Reason? So I've got 2 lines that are to the same line, correct? Both of these are parallel to P, so if 2 lines are parallel to the same line, They're parallel to each other. That's our reason. If two lines are parallel to the same line, they are parallel to each other. Well, per the theorem, if I got three lines parallel to each other, I do, and they cut off equal segments on one transversal, then class, they
Cut off equal segments.
on
Any transversal.
other transversal, right? If three or more parallel lines, I got three. Cut off equal segments on one transversal, I got that. Then they cut off equal segments on any other transversal. What other transversal, Ethan?
JT.
JT. So what other segments must be equal, Ethan?
JX and TX.
JX and TX must be equal because, it's a long one to write, if, I'm going to write it this way, 3 or more as 3 plus. If 3 or more, if 3 plus parallels cut off equal segs on one transva, then they cut off equal segs on any other transva. 3 or more parallel lines cut off equal segments on one transversal, and they cut off equal segments on any other transversal.
That was long.
Of course, you'll be memorizing that statement tonight as you study, correct? Because that's what you do every night. You study every night, memorize all the statements we say. That's good. That's the way we study. Now, what was I trying to prove again? I'm trying to prove that P bisects JT at X. And I just said these two segments are equal to each other. Well, if two segments are equal, then that means that which divides into two equal segments is a bisector. So therefore, based on the definition of bisector, P must bisect at X. P does in fact bisect TJ at X, based on the definition of bisector. And there we go. For homework this evening, you're going to complete a proof. I'm going to put it on the board for you now. So go ahead and have it on a blank sheet of paper. Copy this proof down. I want you to draw a parallelogram, but I'm going to mix it up a little bit this time. It doesn't really matter how we draw, but we never draw them tall and skinny. We always draw them short and long. So I'm going to draw a tall, skinny parallelogram just to be different. But we're not going to be different in how we name it. We're going to be boring. We're going to call it ABCD. What I'm going to do is I'm going to take any size measurement from A, then take that same size measurement from B, that same size measurement from C, and that same size measurement from D. So I'm going to take equal little segments of these sides and cut them off. I'm then going to join X to Y and D to Z. So we got the picture? We're given parallelogram ABCD with AX equal to BY equal to CZ equal to DW. We, of course, then have the lines drawn WZ and XY. I want to prove that XY has to be parallel to WZ. Given any parallelogram, if you cut off equal segments in succession from those vertices and connect the dots, you will get parallel lines. That's what we're proving. 2 hints. You may want to jot these down, or you might just remember them. Hint number 1, you may want to draw a couple of auxiliary lines. You may want to draw a couple of strategic auxiliary lines. Second hint, you're going to want to use the subtraction axiom in this proof. You're going to want to use the subtraction axiom in this proof. All right, there you go. We'll take a look at that tomorrow. Have a wonderful rest of your day.